it asks you to talk about to sketch a new picture, and this is an enlargement, and you're moving the graph also. And to talk about, for excellence, you need to comment on the relationship between the size of the bridge and the equation that models it. So can you come up with some kind of generalization? Let's take a closer. Here I've drawn another bridge. We need one that spans two places of the river, but still has a height of 2 squares. So I've still got 2 squares there, but my vertex has moved, so I can write the equation for my new vertex. So I've got y equals an a, x, it's from the 0, my new equation, it's moved to the right 1x minus 1 squared, and it's moved up to 7. So that's the equation. I need to find out what a is. Now we've got, again, take a point. I like the point 5, 6. So if I put 5, 6 in the equation, remembering that's my x, that's my y, use equation solver. So I've got 6 equals a, and 5 minus 1 squared plus 7. In equation solver, execute, and I find out that my new a is negative 1 over 16. Now previously, in my previous equation, my coefficient a was 1/4, negative 1/4. So by I've actually made it twice as wide. This graph was 6 squares wide. This is now 12 squares wide. By enlarging it, I've actually just widened it by a scale factor of 2, but I've kept the same height. So from negative 1/4, it's gone to negative 1/16. So that's a quadratic relationship. It's been squared. 4 has been squared to become 16. Now we'll take another look at an enlargement. This time, in this last example, I want to show what an enlargement looks like and the effect of the enlargement on the relationship when we enlarge the whole graph by a scale factor of 2. So my centre of enlargement is here at 5, 0, and I've enlarged it, it's been 3 across here, so I've enlarged that to 6 that way. It's been 2 squares tall, so I've enlarged that by 2, so it's 4 squares tall, and instead of being 3 squares to the left, we're now 6 squares to the left. So overall an enlargement by a factor of 2. And let's have a look at how that affects the coefficient a. So my equation for my new graph, the vertex here has still moved from 0, 0, it's moved across the right 5 and up 4. So I have this equation. I'll choose a point here, I think 0.92 looks to be a fairly good point to put in as my 9, 9 is my x, 2 is my y, so my equation will be 2 equals, again in your calculator, use equation solver, and you've got a 9 here minus 5 squared plus 4. 9 minus 5 is 4, squares is 16, so I end up my a equals a negative 8. So I can see from my original graph, which is down here at the bottom in black, the equation for that black parabola, my coefficient was negative 1/4. So when I enlarged, I'll write this in black, enlarged by a scale factor of 2, my coefficient, the original parabola was, the coefficient was a -1/4, and it went to -1/8. So it was multiplied by a half. Can you see the change? By enlarging by a scale factor of 2, we've multiplied the scale factor by 2 of the graph, but our coefficient has been halved. So that's an inverse relationship that the enlargement has affected. Our scale factor we've multiplied by 2, but the coefficient A has been multiplied by a half. So it's actually an inverse. 2 is the inverse of a half and 2 are inverses. So have a look also, you can try this on other graphs. When you multiply the graph by a scale factor, what's the effect on the coefficient? Is that general? Can you generalize that for all graphs? And that's the excellence part of the equation. Thank you.